all, I would like to thank Academy for electing me and giving me this opportunity to present my research. Now most of the talks, earlier talks, I attended very interesting talks, and it's interesting to see how other subjects are doing their research, and many of them, they did try to convey their research area via presenting elaborate diagrams so people understand. But in mathematics, it is a bit hard to do. But so here is my feeble attempt. So I'll deal with the geometric ring first. So yeah. So as you said, it's really a feeble attempt because you can see there is a little dark shade on the diagram there. So I copied this picture from a well-known book in algebraic geometry by Robin Harshen. That book is like a Bible for geometers. I mean, so look at this picture, and let me say something about the first one. So first one is a node. So how do I look at this picture? So I see this as a curve sitting in a two-dimensional space, but I can say it algebraically. This is two-dimensional space is represented by two in variables x and y, kxy, and the node is the zeros of this equation, xy minus x6 minus y6. So zeros of this polynomial is my node. So that's the way we present. So this is my geometry, and this is my algebra here. So now, so this is two-dimensional, and there is a one curve gives a one-dimensional variety, one-dimensional object. Okay, the same thing you can carry on any dimensional. So here what is happening? You have three-dimensional space x, y, z, and you have equation x square plus y square minus z square, and zeros of this will be a conical double point. So this is an infinite space actually, just a curve. So now if I take a zero of a polynomial in three-dimensional space, the answer is going to be a two-dimensional surface. I mean the surface, that's what. So this you carry forward, and for any higher dimension. So what is happening? You have this is called a ring. Polynomials, so quotient of a polynomial. So you have n variables, x1 up to xn, and you take some number of polynomials, f1 up to fm, and take the common zeros of that polynomial. So that will give you xr, which is a space, a kind of geometrical space sitting inside an n-dimensional space. That is what it is, xr. So this part perhaps you can ignore. So what is there? Like that was a curve earlier we saw, and xr was a surface. And if I take a point in xr, it corresponds, say, a1 up to an. So it will be, I can think that as a common zero of the equation x1 minus a1, xn minus an. Because if I look at the zeros of these common zeros, my point is going to a1 up to an. So bigger the number of variables, the smaller you're going to be a space, because you have to take the common zeros of that bigger variety. So that now we will stick to the situation of as follows. You'll have a ring R, something like this. Generally we take Noetherian ring introduced by Emmy Noether, but here just to convey better to the general audience, you can think it this way also. It's a quotient of a polynomial ring. So, and this is also called quotient of a polynomial ring, means if I have a polynomial ring in n variables, and when I say quotient, that means I am declaring this f1 up to fm to be 0. So in yesterday's talk, you already have seen a quotient of a ring. You had a z, and you had gone modulo 2z, and that the person called it z2. So there the 2 was declared as 0. So that's why the z mod 2z has only two elements, 0 and 1. After that, everything can be identified with 0 and 1. So today I will be talking something like z mod pz, where p is a prime. So z mod pz will have only, say, p minus 1 elements, because they just keep getting identified. P plus 1 will get identified with 1, like that. So this is my prototype. So this is it will be R, a ring, and there will be associated space xr, and if I take a point in xr, it will correspond to a maximal ideal. So that's what we do. So we build spaces from algebraic equations or rings, and algebraic geometry, as they say, is a subject which builds geometry from algebra. So this is what we do. So what actually algebra is or algebraic geometer does is this. You have a ring. So ring is something like, as I remember, it's a quotient of polynomial ring is an example of a ring. You have a ring and you want to study ring. So you attach a numerical invariant to the ring by just taking XR and a point at XR and looking the property of the ring in the neighborhood of that point, and then you try to realize the same property holds for entire XR or R, and this is called local global principle. To study the entire XR, you locally study, and the property is such when it holds locally is going to hold if a property is good enough in the neighborhood, and then you declare for entire ring. That's called. So this is not always achieved, but many properties it is achieved. So today I will give an example. So this is numerical invariant. So the choice of numerical invariant you make depends which property of the ring you want to study, of course. So I will recall one such invariant. So remember, your ring was again a ring R and M. So R will correspond to the space XR and M will correspond to a point on XR, and you want to study property of XR in a neighborhood of this point Xn. So what you do, ring is of dimension D. So for example, a polynomial ring in 2-dimensional was a ring of dimension 2. So and M is one of its maximal ideal. So given such a pair, you attach a number. It's called Hilbert-Samuel multiplicity of R at M. So this is a length of R mod M to the power n. So M is an ideal or a set of polynomials, and you multiply n times. So those kind of polynomials. So R mod Mn. So M is a maximal ideal, so R mod M is a field. So R mod Mn is a vector space, finite dimensional vector space. So I can talk of length of this vector space and go modulo these numbers, that is for different regions. So d factorial upon nd. So this limit actually exists. So this is called the Hilbert's, it's called multiplicity of the ring R at M. So what this number detects for the ring, it is telling you the singularity of XR at the point Xm. So this is always a positive integer. So we again go back to our first slide. So here look, so here this is a node. So at any point if I take and compute my E0, answer is going to be 1. E0 is always greater than or equal to 1. So it's going to be 1, but at this point my answer will be 2. Similarly, at this point, which is a triple point, the answer is a 3-dimensional. So this is E0 is 3 at this point, but all other points is going to be 1. So this is more the multiplicity, higher the multiplicity, more your singularity is going to be complicated. So this is a numerical invariant exactly measuring it. So this is a, so for us this is a very nice invariant. There is a cohomological tools various attached to study this, and looking at those equations I can right away tell you what is E0, the way it is arranged. So it's a very well studied invariant. And for resolution of singularity, this is often used. Resolution of singularity means if I start with a ring and which has a singularity, we would like to go compare it with another ring which is images this ring such that that ring is singular, good enough. So resolution of singularity, you keep constructing rings, tower of rings where your E0 at various points keeps dropping till it comes 1. So ring is regular everywhere. So that's a rough idea. Okay, so this is one. Now I mainly work in positive characteristics. So what is a positive characteristic? So yesterday's talk, as I said, you have seen a positive characteristic ring which is characteristic 2. So this is Z mod Pz is of characteristic P, characteristic Z is 0. Formally you want to define, so you can say a ring is, characteristic of the ring is the least positive integer such that M into 1R is 0. And if you do not find any such number, then its ring is called characteristic 0. Actually it should be of infinity strictly speaking, but it is 0. So like a rational number is of characteristic 0. So why we look at this ring actually, this so this is because many times it's easier to solve problem by going mod P, it's called reduction mod P techniques. So one example we have seen in our like MSc course in if mathematics or undergraduate course is Eisenstein's criteria. So this is you have a ring polynomial in one variable a n x n, a n minus 1, a 0. Suppose if I am able to find a prime number here such that p divides this up to all a 0 to a n minus 1 and p does not divide the top coefficient and p square does not divide the constant coefficient, then your fx you cannot write as a product of two polynomials in rational numbers. It is a very easy enough test. So for example, I just write this polynomial 120 degree and I say it is irreducible polynomial right away just looking at the Eisenstein's criteria. And if I wanted to give you a proof of this theorem, I could have fit in this slide actually, few lines. So proof is very small. So the proof is going reduction mod p. You start with the integers, but you are looking at the image of smaller ring and you are deducting something. So this is nice thing. So okay, so before I come to this number, so reduction mod p, when we say lot of things go easy on because you have gone reduction mod p, but many times going to reduction mod p can be working characteristic p can be harder. The reason is that when you are going mod reduction, you cannot cancel out elements now because your p is 0. So cancellation is a problem, unlike you work in a field of characteristic 0. So if I say lambda 1 into lambda 2 is 0, so lambda 1 is 0 or lambda 2 is 0 like that you have to be careful, and lot of funny things go wrong when you are in characteristic p here, but characteristic p has one thing which characteristic 0 ring does not have. It has a Frobenius map. So Frobenius map is a map between ring to ring or XR to XR you can say, where R the ring is self map. So x goes to x to the power p and it is a ring homomorphism. Means x plus y, if I take and raise to power p, answer is x to the power p plus y to the power p, which will not happen in characteristic 0. So this is a ring homomorphism. So this we take advantage. So now analogous to usual multiplicity, take a R ring R, so you have XR and M a point, and suppose characteristic of R is positive and dimension of R is D, then you associate a numerical invariant EHK RM. So it's a real number greater than or equal to 1 here. So it's called Hilbert-Kunz multiplicity, and this is given exactly same length of R, but instead of m to the power n, I am taking nth Frobenius iterated power on m. That is what I am doing. So if I just want to look in algebraic fashion, I can say m to the power n is x to the power p, and if x belongs to m, x is not a variable, it is element of m. So this has a interesting history, depends how much, okay, so I do not have much time, so I will not go into that. So this is actually 60s it was proved the limit does not exist, and 80s it was proved actually limit exists by number theorists, and then the whole new area started. So why is it interesting first of all? So this is a subtler invariant, it involves a characteristic of the ring, and in that means it tells me characteristic p singularity of the ring, it will carry the information. That's so first thing first. So if I have a EHKR is greater than or equal to 1, but if it is the least like usual multiplicity, then R is smooth, same thing. Okay, then in the situation R graded ring, so graded ring is a common thing which I have mainly geometers deal with. So R is a graded ring, so you would have a proj R. So proj R is like a XR, proj R is another topological space or geometrical space you can say, which is compact. Once you are compact, it has many other numerical invariants which show up non-trivially. So it give a lot of information about proj R. Now generators of M will give me a bundle V on proj R. So it's like a locally line sum of bundle means direct sum of copies of the same thing proj R. So you can say locally. So this number EHKRM, so this gives me a information on Frobenius semi-stability. So whatever it means, how this bundle behaves when you take a higher and higher Frobenius and pull the bundle up. And in fact, on the plane curve is gives me numerical information about how much it destabilizes and at what stage it destabilizes, all the information. This was a nice result, this was a characterization which is very surprising, because for vector bundles to compute Harder-Narasimhan filtration or this kind of check, it was a difficult thing for. So this gives right away, because Monsky had computed some examples and they gave a surprising example for the vector bundle people. Things may go wrong, certain things when you go reduction mod P, so which they didn't expect. So the thing that time when Monsky did, he asked the question, is EHK rational number? Not, he's asking very less, he's not saying is it integer, he's saying is it a rational number. So this was 1980 and 2005. One answered if R is a graded ring of dimension 2. 0 and 1 it is trivial, there is nothing new happening, but this is the first non-trivial case. So that was, you can see the time gap actually. So in between entering, what happened, people did compute examples including Monsky, but those examples are very specific. So the problem is you take like a polynomial ring and n variables and go modulo simple equation x1 square plus x2 square like that and say what is EHK. And this ring is, mind you, is the simplest class after polynomial ring. People try feeding the computer will tell you some answer at a level n, but it is not giving you the entire picture. And I want a picture in the limit case when what happens when n goes to infinity, and that didn't occur. So this is, so the way we obtained this question was, attack this question was actually via vector bundle. That's how we got the answer. So this is what we approach, and that's why the answer is so late actually. So here, I am going very fast now. So as I said, to compute HK was very difficult, but unless you compute HK, how do you conjecture any property about that invariant or guess? That was difficult. So this is what in 2018, one said perhaps if I take a graded situation which is geometric situation, so I can apply tools from geometry, that's the idea. Instead of the ring EHK, which is just a real number, construct a continuous function such that the integral of that continuous function is your EHK. So what is happening, this doesn't come from nowhere. Basically you are looking at, R is a graded ring, so you are taking limit over each graded pieces and finding it makes a continuous function, and then you are integrating that function. Here you are first adding the integrated pieces and then you are taking the limit. So it's a reverse operation. So look at this way. So that was the one thing. yeah. So what's the advantage? This is, you can apply for Fourier transform and evaluate at 0, your answer is EHK. So EHK behaves like a point on a function. So what was the advantage of this function? It's additive multiplicative. It's no more difficult than EHK and it carries more invariant. So this is a result of Watanabe and myself. So if I take a maximum support of the function, it's a compactly supported. So you look at the point after that it vanishes, it's going to have F threshold. F threshold is something which comes characteristic P analog of characteristic 0 called log canonical threshold, etc. So there is again related to resolution of singularity, this thing. So they had this, and their question was, can a threshold have a limit point? Because log threshold has a limit point, those have actually. So answer was yes. In fact, no, log canonical threshold discrete set, they do not have limit point. So they did ask this question, and the answer was yes. Again, you are associating the support of FRI with vector bundles, and then I apply the Giesiger's example of this funny behavior of vector bundles. So you get answer yes, actually it does fail. So in projective variety, so this is nothing to do with characteristic now. I have a convex polytope, just it's a very combinatorial picture. I have a convex polytope. So this number, the growth of EHK exactly characterizes when your convex polytope going to tile the space. So this has nothing to do with characteristic, that's a very funny. So the EHK growth is the least if and only if it tiles a thing. If it is not, then it's telling you how much overlap is going to take place. So like dimension 2, there are only 2 polytopes like that. It is hexagon and the squares, they will tile the thing. So this is with my student Mandal. So see, this one is tiling. However, this which comes from the polynomial rings in 2 variables, this is a very good P2. So this is not going to tile the space. How if I magnify this more, it's going to, there will be overlap. So is EHK, that thing will actually be bigger. So these are the properties I am telling. You had EHK, you look through the prism of the HK density continuous function, and you got more information. So I think I will stop. My time is up. Yeah.
We have some.
I have a very generic question actually, because what you talked of E naught or EHK, these are invariants which were proposed, from what I can see, proposed by Hilbert or Hilbert and Kunz. Is that correct?
No, it's not proposed by Hilbert. Hilbert was the first one to look at the length function or this. So that is Hilbert-Samuel multiplicity. So it's analog of that. So this this was actually this length function was looked by Kunz. It was a funny story because he was the first, one of the early person to realize that I should use characteristic P to study various things in algebra. He was the pioneer, and he looked at this limit function. Why did he look? It's not clear. He found a count. He said it doesn't exist, and he stopped there. And the number theorist Monsky, who was looking at P growth of the ideal class group, in this thing. So he said perhaps I should formulate my problem in terms of algebra, and he came with this length function.
Okay, no, actually I wanted to continue with, at first that was just my question really is that in general in physics, with what Emin author taught us, that invariants are associated with some properties, in our case properties of some functions. So here what you are really showing us, at least if I understand this correctly, is that studying these invariants, which are, you are getting more information about your the structure, mathematical structure that you are investigating. So the question I have is that, is there a procedure by which one constructs these invariants? Or are these just, is it an art that people say that this particular invariant is a very good guy to study because that's going to...
what people try to define is a set of invariants, and they try to say what can they, using that what can they do.
Yeah, but my question was, is there a process or is there a principle by which one can construct these invariants? Because,
principle is... Yes. Yeah, it's there has to be principle, because you want to see how does it behave locally, globally. I mean, how accessible it is. If it doesn't give any information or it is very difficult to compute, then it's a dead case actually. So sometimes it relates. So HK multiplicity is one case, it actually related to vector bundle right away. I mean, that was very surprising, because what vector bundle got to do with this? So in fact, many young algebraists are actually studying vector bundles. That's nice. I mean, and this invariant, so now this invariant coming HK multiplicity, I am trying to relate with a continuous function, and actually I believe, in fact, that now analysis will enter. And in fact, I was trying to compute quadric hypersurfaces, and there it entered, because HK multiplicity, as you know, is hard to compute even for that simple case. So what you are looking, you know some data about the continuous function, but you don't, it pinpoints which are the difficult spots in that particular case, quadric hypersurface. So this is saying those difficult spots are of measure 0. So I can ignore them. So there the analysis has entered and tells me that I can remove that. Yeah.
From resolution of singularity you started, I could see something then. I didn't follow it. Now there was a big jump to tiling of convex polytopes.
Yeah.
So is there a way of, how do you come to polytopes when you start thinking about, because polytope, like tiling the plane, for example, is very fond of...
Not tiling the plane, any dimension.
Physicists are fond of tiling the planes, Penrose tiling and so on. Mathematician Penrose. Is there any connection of that? Can one approach the problem? Sorry.
No, because tiling of polytope has nothing to do with resolution, because I'll tell you, because projective, I gave example of a P2, that is example, that triangle I gave. So that will never tile. It's the best ring we have, but it's never, it's already, it's a smooth thing. There's nothing, but it's giving problem. But on the other hand, other rings of, I have not written those pictures, they are tiling very well, and they are not such a good rings like P1 cross P1. So that is not connected actually. I don't see it as
Yeah. Thank you. Any other questions? Yeah. Thank you very much. Thank you.